November 2016. A massive steel arch has moved slowly over the site of the worst nuclear disaster of all times. This is Chernobyl, the site of 4 of the former Soviet Union's nuclear power plants, located on the Ukraine-Belarus border. On the 26th of April 1986, an explosion at one of the plant's 4 reactors sent radioactive debris into the atmosphere and contaminated most of Europe. The hastily built concrete and steel sarcophagus has survived till now. With a massive financial investment from the European Bank of Development and Reconstruction over the last 20 years, the international community has worked with post-Soviet Ukraine to deliver the largest ever mobile structure, a massive arch that has been slid over the sarcophagus in order that the aging radioactive carcass can now be safely dismantled and disposed of.
May I have your attention, please? A fire emergency has been reported in the building. While this is being verified, please leave the building by the nearest exit.
1:28 a.m. on the 26th of April 1986. Chernobyl. Scientists are doing tests at the nuclear power station with 4 reactors, one of the technological jewels of the Soviet Union. They want to see if the turbine can provide enough backup power during a blackout to keep the cooling water flowing while generators kick in. A sequence of errors leads to a buildup of steam in the reactor cooling water. There are 2 explosions that literally blow the top off the reactor into the night sky. Over the next few days, radioactive material shoots into the atmosphere. It not only falls on the surrounding countryside, but is carried by the winds as far as Finland and Italy. Soviet soldiers and pilots volunteer heroically to stem the radioactive fallout and then to build an enormous steel and concrete structure over it. The whole area is evacuated as the plant continues to unleash 200 times more radioactivity than the Hiroshima and Nagasaki atomic bombs. It is the most catastrophic nuclear accident ever, a disaster that will kill hundreds and create permanent ghost towns across a wide swathe of eastern Ukraine. Today, the protective structure built to contain the radioactive material, known by its Soviet-era name as the object shelter, or more commonly as the sarcophagus, lies under a massive steel arch, hermetically sealed and built to allow work on the steel and concrete structure that still houses the radioactive fuel rods that were the core of Reactor 4 at the Chernobyl power station. The explosion in 1986 released just 3% of the radioactive material of Chernobyl into the atmosphere. The remaining 97% lies beneath the deteriorating concrete shell of the sarcophagus. It is one of the world's most dangerous ticking time bombs. The new containment structure is designed to reduce the risk of another future disaster.
The whole program that we are financing there, the so-called Shelter Implementation Plan, includes much more than only the construction of the new covering. There were quite a few preparation measures and infrastructure that wasn't present here and had to be financed. And the whole program costs a little over €2 billion.
Since Roman times and even before, everyone knows that the arch is an extremely effective structure in terms of weight distribution.
The nature organizes cooling of the core of the reactor. It was maybe complicated to explain, but in reality, From day to day, the temperature of the core decreased.
The massive arch that now covers the old sarcophagus is the result of decades of planning and designing, not only in conceptualizing a new containment structure, but also in lifting it and moving it over the decaying concrete monster. Building it directly over the sarcophagus presented a significant health hazard for workers. So the largest ever man-made object to be moved over land had to be built at a safe distance from the old structure and then had to be slid into place. It was a mega move of a massive half-dome and an amazing piece of engineering. Balthasar Lindauer is overseeing the final phase of the huge job that the European Bank of Reconstruction and Development has undertaken over the last 20 years. The construction of the arch, the destruction of the old sarcophagus, and removal of the radioactive material.
The new covering by itself cost around 1.5 billion euro, of which the design effort surely is the smaller part, even though it requires a lot of people to work on that. But the more expensive part is the construction. And for that, the 1.5 billion euro were mainly costs. We are then ready. As I mentioned before, the EBRD is ready with the project. After, it will be handed over to Ukraine after completion of all works.
The massive engineering effort that over the last 20 years has gone into building the Arch of Chernobyl, known as the new containment structure, was possible because the sarcophagus built over the radioactive reactor held up for so long. Nikolai Steinberg was in charge of the project from the week after the disaster.
We start preliminary works in May. We cover the site around unit number 4 and unit number 3 by concrete up to 3 meters. By the end of May, maybe. It was made decision by top management of the Soviet Union that Ministry of Middle Machine Building was appointed as responsible for design and construction of sarcophagus. In '86, we spent 5 months for construction, design and construction. An absolutely incredible situation.
Today, the structure that Nikolai Steinberg hurriedly threw up under mounting international pressure and under the watchful, worried gaze of the whole world is being dismantled and replaced by a new, safer steel building soon to be handed over to the Ukrainian government.
Here it's about a step-by-step approach. The state of knowledge about the reactor and the shelter that was built wasn't that good. So the first step was to actually develop a detailed plan how to approach this problem. Surely we are dealing with a destroyed reactor. A majority of the radioactive material is still in the reactor, and around it we had relatively high radiation exposures.
The high gamma-ray radiation levels close to the reactor dissipate with distance from the radioactive core. This led to fundamental consequences for the project.
That makes this operation much more complicated and more expensive than other construction sites. And an important factor was that we decided, and this was an important design step to say, we built the concealment aside from the reactor and then pushed it over. The main purpose of this was to reduce the radioactive pollution for the workforce.
In 2007, the first pieces of this immense steel construction began arriving from Italy. They had been built based on French designs produced by powerful computer programs. Once on site, the pieces had to fit perfectly. Everything had been calculated to the millimeter. Even the lifting processes that eventually moved the arch over the steel and concrete sarcophagus of doom. On the 25th of April 1986, tests on the backup power system require a lowering of the power produced by reactor number 4 of the Chernobyl power plant. But a request for more electricity from Kiev delays the experiment, and an inexperienced night shift team first remove and then reinsert control rods that reduce the uranium rod reaction, provoking first an uncontrolled drop and then a rapid rise in the reaction, and causing a massive head of steam to build up in the cooling water that, at 1:28 a.m. on the 26th of April 1986, eventually blows off the top of the reactor core.
So its problem was connected to thermohydraulics and physics of the reactor. Some mistakes of personnel, jointly with design mistakes, realized in explosion. For personnel, it was a situation when they should implement all their knowledge and moral condition to be in the real war.
The Soviet government evacuates 360,000 people over the course of the next month, leaving small towns like Pripyat completely empty. Ghost towns frozen in time. Eerie snapshots of life interrupted by the worst nuclear disaster the world has ever seen.
For first 6, 7, 8 months, in reality in Soviet Union was created the system of Chernobyl issue management absolutely adequate to situation in the war.
46,000 people used to live here, shop here, go to the theatre here, and enjoy their days off in the fun fair. Before the disaster, 1,000 babies were born here every year. Pripyat, like dozens of others in the 100-kilometer-wide exclusion zone, is just a ghostly reminder of the cities that once were. Now being overtaken by forest, flora and fauna that instead have survived against all odds. As the disaster unfolds, more than 600,000 pilots, soldiers and civilians, known as liquidators, begin stemming the flow of radioactive material, sacrificing themselves to drop hundreds of tons of cement onto the reactor from helicopters and building steel and cement structures around it to contain the dust. Hundreds die of radiation sickness. The heroes of Chernobyl are commemorated outside the Chernobyl fire station and in the Chernobyl Museum in Kiev.
Main priority was safety, how to decrease level of occupational exposure, decontamination of the site, restoration of the unit, because we have very strong task for us to return unit number 1 and 2 in operation by the middle of autumn. So it was our responsibility. In May, my task was decrease as much as possible number of people at the site.
12 years after the disaster, The political situation of the Ukraine changed dramatically after the fall of the Soviet Union. The highly contaminated site of the Chernobyl disaster and 2 other reactors that still pumped power to the rest of Ukraine were identified as new priorities in the development program for Eastern Europe.
Es ist natürlich eine große Herausforderung für einen Staat, der zu dem Zeitpunkt.
It is, of course, a big challenge for a state that, at that time, was newly founded and that had economic difficulties to be confronted with such a unique and grave problem like Chernobyl. We also felt that during the implementation of the project, it was a huge challenge in many respects, regarding the training of the people that are needed here. Also for all possible financial support that is necessary for everything around the project to make sure that Ukraine can master this challenge. With time, we built a very good team, and we're pleased with the collaboration with Ukraine.
Wir sind hochzufrieden mit der Zusammenarbeit mit der Ukraine.
The European Bank for Reconstruction and Development stepped in, with 45 donor states. But there were many key details that had to be fully explored before the project could be set in place. The company that won the contract to actually build it was a consortium between 2 French engineering companies, Vinci and Bouygues. They formed Novarca, the company that built the arch and today manages the final phases of the project. Cyril Fagier is the project director for Novarca.
Welcome in the Arch of Chernobyl.
The general dimensions, 108 meters high, 260 meters wide, between these plinths and the ones to the south, and then 160 meters in that direction, as we cover the whole object shelter, the reactor, and the whole thing weighs more than 36,000 tons. When we skidded it, it weighed 36,000 tons, and in the meantime we've continued to add equipment and tools, so now it weighs a little more. But that's the general idea, nearly 40,000 tons.
The arch is big enough to contain the whole of Notre Dame Cathedral in Paris. Over the 10 years of construction, the new confinement structure transformed an ambitious engineering project into the world's largest land-based movable object. It had to be built where workers would be safe from radiation, at least 150 meters from the radioactive core.
Quand les équipes de Vinci et Bouygues sont arrivées donc en 2007, ils ont trouvé un terrain.
When the teams from Vinci and Bouygues arrived here in 2007, they found a contaminated terrain with radioactive objects. So the first stage was to clean, first of all for worker safety, and then to build a platform on which we could work. We even built a thick concrete platform to stop all the radiation coming up from the Earth from reaching the surface, and that allowed us to work in a completely safe environment.
De remonter. Donc ça a permis de travailler dans un environnement qui était absolument sûr.
The land is slightly sloped, so designers had to take the local landscape into consideration to give the arch perfect vertical stability. The plan also involved skidding the arch into place, using skid shoes set at 45 degrees to the surface to take the full load of the arch. These tracks had to be designed into the project too. The available area to build the concrete foundations of the construction yard was not large enough to house the whole of the arch, so the French engineers came up with a novel solution.
Rather than build a concrete platform that was the size of the whole arch, which would have been enormous, especially taking into account the contamination of the Earth, we decided to build the arch in 2 pieces. A first semi-arch was built, and this was moved, and then we could take full advantage of the special foundations, and also the famous lifting towers that were already in the right place, to build the second half. The second half arch. These 2 half arches were then brought together. They were connected. Here we did have some welding, but it was planned, and it's the only place where we had to use welding in the whole of the construction.
The arch that today stands over the Soviet-era object shelter, or sarcophagus, is designed to survive for at least 100 years. Even though the half-life of the radioactive material will make the site dangerous long after that. The designers took into consideration the potential threats from climate change, over-budgeting for extreme weather. It had to survive Force 3 tornadoes and temperatures as low as -40 degrees centigrade. The arch shape makes the structure solid, with the entire weight of the steel and concrete resting on the plinths on the concrete floor specially built to house it.
La première chose, c'est qu'on a décidé de construire l'arche.
The first thing we decided was to build the arch several hundred meters away from the reactor. Why? Obviously, because the further we are away, the lower is the radioactivity. So we had to work far enough away to allow us to work in normal conditions, so as not to have limits on the length of our working hours.
The arch not only had to cover the entire old sarcophagus, but it also had to allow workers to dismantle it remotely, without being exposed to the toxic dust and rays that the reactor emits. To do this, the planners decided to install 2 remotely controlled cranes that could lift toxic material and have different tools attached to them. This, of course, would increase the required resistance of the arch itself. Once the overall principles had been established, it was up to the individual engineers to come up with a robust design structure that would do the job. The sustaining element of the new containment structure had to hold up the inner and outer surfaces, plus the 2 gantry cranes. The French engineers came up with a trellis structure made up of tubular steel elements that used intersecting pressures to offload the weight onto the foundations, very similar to the world-famous steel trellis Eiffel Tower in Paris.
La structure de l'arche, en réalité, elle est constituée d'une structure primaire, c'est vraiment la structure porteuse.
The arch structure is actually made up of a primary structure that carries the weight and through which all the forces are channeled. This is a trellis with a distance between the upper chord and the lower chord of 12 meters. This constitutes the annular space, and you'll see it later. Then we covered the primary structure with a secondary structure with curlings that allow us to position the cladding, the stainless steel skin, which is a little more complex than it seems, as it is really a multi-layer surface.
Qui est un peu plus complexe que ça, parce qu'en fait c'est un multicouche.
The heavy lift company that Novarka brought in to move the arch they had designed was Mammoet. The company had become famous for raising the Kursk submarine, using massive strand jacks, a tool that would play a key role in this massive move too.
En réalité, quand les équipes de Vinci et Bouygues ont conçu cette arche,
In actual fact, when the Vinci and Bouygues teams designed this arch, they designed it together with the people who would work on the construction site and with the subcontractors that have the expertise. All the details are designed with the tools we'll be using in mind. We can't design such a concept and then wonder how we're going to actually build it on site. It has to be done as a partnership and hand in hand. And it worked very well.
Ça doit être fait vraiment en partenariat et main dans la main, et ça a très bien fonctionné.
The tubular steel structures were built in Italy by oil platform specialist Cimolai. They were designed to fit each other with incredible precision, with flanges and pre-tensioned bolts holding them together.
Obviously, this whole structure was designed on a computer, which is traditional now. But we also built computer models, because we had to be absolutely certain that as we were putting together these thousands of pieces in the construction yard, they would slip into place, and each hole match up with the facing holes, to the millimeter. So the assembly was carried out virtually in the design bureau in Italy, and that allowed us to build the structure in record time.
Parts for the lifting towers were delivered too. These were designed to be built on a skidding system that allowed them to move outwards from the arch's centre line. They had a vital role in the overall plan.
Tout a été fait par boulonnage. C'est la technique de boulon précontraint.
Everything is held together by bolts. The technique uses pre-tensioned bolts. So the bolt is pre-pressurized and compresses the two plates, so the forces are exercised through friction. A funny detail is that there are 700,000 bolts in this arch. 700,000 pre-tension bolts have been used to hold this arch together, and this works extremely well.
Once the central part of the arch was finished, the covering panels had to be lifted onto it by cranes. Keeping control of them in the high winds was an extra challenge, and they were large enough to catch the wind and fly like wings. The outer panels were built first, to give protection to workers as they built the inner surfaces. They were made of stainless steel. The inside and outside surfaces were different. The inner surface was beveled so as to reflect the gamma rays internally, and the outer surface was as smooth as possible to keep the rain and snow off it.
There's an inside and an outside. The skin is stainless steel, but the outer surface also has layers of watertight material and isolation, which makes the sandwich slightly more technical.
None of the movement would have been possible without the intervention of vertical lift by strand jacks and horizontal slide by skid shoes, technologies mastered by Mammoet. The key to building the arch in segments was being able to lift the semi-arches, and this could only be done by lifting towers.
So the construction method was a real challenge. How do you build a structure that is more than 100 meters tall, 260 meters wide, without using gigantic tools or cranes? So the teams, the design teams and the construction teams, that's what we call the constructability study, decided first to build the central part, the upper part, the part that today is 100 meters high, to build it on the ground. Why on the ground? Because it's easier. We need small cranes. It's safer. In safety terms, it's better to work close to the ground rather than at very great heights.
The segments had to be lifted and moved. The engineering solution was complex and daring.
Then we would lift this central element using the lifting towers, and then with this element suspended, build the elements on either side, the elements of the arch on either side, then lift again, and then build the last elements of the arch that allowed us to rest the arch on these plinths.
The key element in lifting such a heavy weight are strand jacks. These are hydraulic lifting devices that spread the weight among many separate steel strands and then apply hydraulic force to lift the weight. Steel teeth bite into the strands and hold them as the hydraulic pumps fill once more to begin a new lift. They are slow but powerful. Especially, they have to work in perfect sync, all together, to get an even lift all over the surface.
Les tours ont été livrés un petit peu comme l'arche, évidemment, avec des membrures évidemment bien plus petites.
The towers were delivered like the arch itself, obviously with shorter beams, also held together by bolts. So the lifting technique that was chosen was the strand jack, installed by our subcontractor Mammoet, each of which allowed us to lift weights up to 15,000 tons. We invented a new method, so we designed a system by which we could skid or move these towers from one position to the next. There were 3 different positions.
D'une position à l'autre, effectivement, il y avait trois positions différentes.
The months went by, and the first segment was ready to be lifted. But first, the gantry cranes had to be installed. Then came the day for the first mega lift. It was a slow operation, and controlling it was a challenge. Giant strand jacks mounted on 10 towers pulled for 12 hours to get the roof into place. While the middle segment of the arch was set in place and rested on the concrete foundations, as the towers were skidded outwards. Cables tensioned by strand jacks kept the edges of the arch from bending outwards as they were lifted, to ensure perfect fitting of successive segments as the top was lifted to its full height. The operation was repeated one last time, and the lower segments of the arch were built and lifted. But this time, they were positioned on the upper surface of the skid shoes that had been laid to transport the mega arch over the aging Chernobyl sarcophagus and the dangerous cargo encased below it. The first arch was moved towards its final resting place to make space for the second half that went through the very same process. In all weather, winter and summer alike, the workers of Novarka and Mammoet worked together to move the project forwards. In all, up to 3,000 workers were on site at the height of activity. There were no accidents. It was literally a mammoth task. On the 22nd of November 2016, the arch was ready to be slid over the brittle and decaying remains of the sarcophagus. It was the make or break moment of the whole project. The arch was ready to be slid over the sarcophagus, the symbol of the worst nuclear disaster ever.
Der Auftrag für die EBRD ist die Errichtung dieses.
The task for the EBRD is the erection of complex systems that are in the confinement structure. For example, the ventilation system is extremely important, fire protection measures, the crane system that we need for that. Everything that makes this system what it is our responsibility. As soon as the confinement and the whole plant is fully finished, we will hand over everything to the Ukraine authorities that will use these systems later to remove radioactive waste and strip down the reactor itself over a long period of time.
Den Reaktor selber im Laufe der Zeit über große Zeiträume zurückzubauen.
The whole arch weighed 36,000 tons, and the intersecting beams meant that all the weight lay on the outer surface of a trench built at 45 degrees to the horizontal. The entire weight of the structure was held in place by skid shoes. Skid shoes are able to move the loads they carry by pushing against Teflon sleepers that they literally skid over. Each of the skid shoes moved at 10 meters per hour, slowly but surely, towards the sarcophagus. By the end of the seventh day, it was in place.
Donc, ce qui est remarquable ici, c'est en fait.
What we can see here is the structure of the plinths, and they're technologically relatively simple. We see these plinths holding up great works of art, and the whole of the arch's weight is offloaded here. And when I say weight, I'm talking about the arch's own weight, the weights from external factors, earthquakes, winds, and so forth, but also of equipment, because inside the arch, and you'll see it later, the main crane system, so we have two enormous gantry cranes that weigh 1,500 tons each, two monsters. It's very interesting. So the weight of the cranes and the weight of what they carry are spread through the structure of the arch and lie on these plinths.
Les charges qu'ils portent redescendent également via la structure de l'arche sur ses appuis.
Now the skid shoes had to be removed, and the weight of the arch rested on huge plinths built into the diagonal wall of the foundations. Today, the 30-year-old sarcophagus is completely covered by the new structure. And while the surrounding countryside is eerily, deathly quiet, the site itself is a hive of activity. The gantry cranes are active all the time, as workers consolidate the building with a containment scaffolding and cover it so that eventually the radioactive core can be removed. This structure represents a 30-year effort to reduce the future risks posed by the worst nuclear disaster of all time.
The main task, main goals for construction of new safe confinement was to protect environmental from distribution of radiation from unit number 4. Unfortunately, study of this object, from my point of view, for the study spent so much time, so 20 years for study, design and construction. Once more, I would like to underline, in '86, we spent 5 months for construction, design and construction.
Today, the new containment structure covers the Chernobyl sarcophagus that still contains what is left of the reactor number 4 of the Chernobyl power station. The massive trellis of tubular steel arches can be seen from the stairs that lead to the upper gallery. Activity around the old concrete and steel building is intense. The Chernobyl Arch is also equipped with a state-of-the-art control room, where every environmental parameter can be monitored. A massive air purification system ensures that no radioactive material from the work going on inside ever gets out. Here, HEPA filters are activated at any time there is a rise in contamination. And as workers climb the 100 meters to get to the top of the building, where the gantry crane is operated, the skeleton of the arch becomes visible, with the thousands of bolts and high-tech steel beams. It is a confined world of its own.
Notre contrat, le contrat de Novarca, des sociétés Vinci et Bouygues.
The Novarca contract between the companies Vinci and Bouygues will cease when we hand over the keys and train the teams of Chernobyl power plant to use this tool. So it will be up to them, maybe through subcontractors, to begin the second stage, which is dismantling.
D'amorcer cette seconde phase qui est le démantèlement.
Now the new safe confinement, as it is called in English, has a lifespan of 100 years and allows then with time and planning to determine the next steps and to conduct these steps. A concept has to be developed. Which parts of the reactor have to be removed? Which radioactive materials shall be extracted from the reactor? A lot of other questions also have to be solved, and that, for example, where the material is to go after it is being extracted from the reactor. Since we developed a safe system with a lifespan of 100 years, these things can be approached calmly.
En réalité, cette arche, elle est conçue pour durer 100 ans. Donc, on parle...
In actual fact, this arch has been designed to last 100 years, so we studied earthquakes going back several thousands of years to be absolutely sure that in 100 years it would suffer no damage. And of course, the big challenge when we say 100 years is the durability of the steel, because we selected stainless steel, and of course, the final user asked us to limit the amount of maintenance they had to do. So we have a structure that over the next 100 years won't need painting.
Et donc on a une structure qui pendant 100 ans n'a pas besoin d'être maintenue, elle n'a pas besoin d'être peinte.
It's a nuclear object, and all people which work at the site should be absolutely ready for any situation and prevent such situations. That's all. It's a nuclear site.
Eventually, all the radioactive material from Chernobyl will be removed to a safe place, a second project to be financed by the European Bank of Reconstruction and Development. Chernobyl's radioactive risks may be laid to rest for now, but the ghosts of Pripyat will haunt Europe forever.
From my point of view, no one other government in the world could decide this problem. It's a reality. In such time, very short time, no one. It's my opinion.
The air, water and soil will always be monitored, even as tourists of the macabre brave all kinds of weather to visit what was once a thriving small town, a proud symbol of successful Soviet society, that overnight became one of the most grim and catastrophic landmarks in all of humanity. Despite the reminders everywhere of how normal life was once here, this place may never return to normal, doomed to exist under the dark cloud of environmental uncertainty forever. Asian shipyards are building more ships than ever, but getting them to Western clients in pristine condition, unscratched and ready for action, requires a very special kind of logistics vehicle to transport them across the world's oceans. Only a very few companies in the world operate ships that carry ships, as well as a number of other gigantic floating objects. This is the story of one of the heaviest lifters on the high seas today, the Hawk. As foreign companies manufacture larger and larger industry components in Asia, and China's economic boom continues, demand for heavy lift shipping capacity in Southeast Asia is at an all-time high, making the region one of the busiest nerve centers of maritime traffic and a center for shipbuilding. The more goods that are shipped, and the bigger the project cargoes are, the more ships are needed around the world. But not all ships being constructed are capable of making a transoceanic voyage. and most customers want them delivered brand new. A handful of heavy lift companies have found the solution for delivering them: ships that carry ships.
We try to plan for the worst and always hope for the best. We will always try to have a plan B and a plan C, sometimes even up our sleeve, just to be ready if something is wrong. Then we are ready. We are always prepared with some backup plan.
The most important to the vessel and to the captain to deliver the cargo in safe and good condition. So if we will see that weather condition not good, and we will wait weather improvement.
Hawk is a semi-submersible heavy lift ship designed to transport heavy loads around the world that conventional ships can't carry. Semi-submersible heavy lift ships have a long and low cargo deck between a forward pilot house and an aft machinery space. The ballast tanks can be flooded to lower the cargo deck below the water's surface, allowing oil platforms, other vessels or other floating cargo to be moved into position for loading in an operation called float on, float off. The tanks are then pumped out and the well deck rises to shoulder the load. To balance the cargo, the various tanks can be pumped unevenly. The Hawk semi-submersible is among the 10 top of its kind in the world, and the biggest in the fleet of offshore heavy transport, a Norwegian company that is one of the leaders in the sector. Originally built as an oil tanker, she was retrofitted by OHT in 2008 and 2009 in order to be the vessel we see today. The vessel weighs 25,600 tons, but when she's sailing, she has 85,000 tons, and if she's submerging, the weight of the vessel is a whopping 130,000 tons, as much as 65,000 large trucks or 800 Boeing jumbo jet planes. Vietnam is a commercial crossroads of Southeast Asia. Bordered by China and protected by the Philippines and Malaysia, it is the perfect stopping-over place for large ships loading and unloading containers and other large cargo loads. This is the port of Vung Tau. The fishing boats and fishing nets of the inhabitants share the sea with hulking cargo vessels from all over the world. In the coming days, the shadow of the Hawk will dominate the landscape. She has sailed all the way from Norway to meet with her next cargo here. Bartosz Kozinski is the loadmaster following the operation. The Polish seaman has been working on ships for 20 years, the last 5 as loadmaster. In the last 5 years as loadmaster, he has loaded some of the heaviest objects on the high seas. He averages about 1 heavy load job per month, but each operation is different, presenting its own set of risks and variables. For this operation, Hawk is transporting ships to the other side of the world, ships that otherwise wouldn't be able to survive a transoceanic voyage, not just vessels that are out of commission or in need of repair, but also jack-up rigs and, as in this case, brand new modular carrier vessels made for navigating rivers and inland seas, able themselves to carry up to 1,800 tons stacked high on their decks. The ships are ready for work and even have their full crews with them.
We are at the DXP yard in Vung Tau, Vietnam, where we came to inspect 3 MCV units, module carriers for our client. Each module is approximately 3,000 module carrier, 3,000 tons in weight, 123 meter long. We will be loading all three of them in a few days from now.
Before inspection of the 3 cargo vessels that will be loaded onto the Hawk, Bartosz heads up a meeting with all those involved in the operation. The 3 captains of the vessels being transported and their crews, who will be hosted on board the Hawk during the transport. But also present are the port authorities of Vung Tau, the logistics directors, the commanders of the tugs that will tow the ships out to the point chosen for loading. All in all, more than 100 people at sea and on shore will be assisting in the operation. Bartosz describes in detail all the phases of the operation, responding to numerous questions, as everyone wants to know the loadmaster's opinion as to how best to carry out their various tasks. The biggest question of all, however, is the forecast. The date has been fixed 2 days from today, but the weather must cooperate.
We came here to make an inspection to see if they are ready for loading, if all preparations were done in accordance with Transport Design Manual. Also to have a meeting with all parties to discuss how the all operation will look like and all the safety aspects, just to make sure that the operation is safe and smooth, that it will go all okay. Since all 3 units they will be loaded on a vessel and they will be staying alongside each other, so basically each unit will be touching each other. We need to have fendering system just to protect them from damage.
Once the meeting is over, the parties head to the vessels already anchored in the port of Vung Tau for a thorough inspection.
There is wooden fenders on the last unit, which is the one completely outside. And we had to check the exact position, that the position of these fenders is in accordance with the design, that they are exactly on the strong points of the vessel, that we will not have any damage, that the fenders will not clash with some structures on the units, that we will not have any problems with the final positioning of the cargo during the loading.
The wooden beams must be laid across 8,700 square meters of deck area. It is perhaps the most crucial aspect of transporting such heavy cargoes long distances. Bartosz and the captain of the modular carrier vessels discuss how best to position the beams based on the measurements taken during the prior inspection.
They are designed to sail in sheltered waters, in closed areas, so rivers, seas like the Caspian Sea, so not ocean conditions. Just the construction of the vessel does not allow for voyage through the ocean. Because even if they were strong enough to sustain the ocean passage and could be towed by a conventional tug, the heavy lift ship is much faster than a tug. It's 2-3 times faster than the tug. So the owners of the cargo, they will get their ships in location much faster, meaning they can start making money much faster in this case. So the time, it's a big factor in here.
Wave limits are also crucial during the loading operations because there are multiple floating objects, the Hawk heaving up and down, and then the vessels being loaded. The 3 brand new vessels, once loaded onto Hawk, cannot bump into one another because they could be damaged before even arriving at their destination.
We don't want to damage the ship, we don't want to damage the cargo. You know, the owners of the ships behind us, they paid for a brand new equipment and they want to have a brand new equipment delivered in a discharging location, so they want a scratch-free delivery.
The forecast continues to worry Bartosz. It is the monsoon period in Vietnam, and hot winds passing through the area can influence the weather and exacerbate unexpected thunderstorms that can be violent and create dangerous swells that put the cargo and the crew loading it at risk. The monsoon in Southeast Asia affects the climate here from May to October, with most of the intense weather systems moving from the Asian continent and then clashing with the humidity of the peninsula, leaving the coastal areas vulnerable to intense storms. The monsoons of Southeast Asia are threatening to disrupt loading operations near the port of Vung Tau as 3 newly built modular carrier vessels await transfer to Europe. The OHT Hawk is charged with carrying out a float-on, float-off loading operation during which the Hawk's deck submerges so cargo can be floated over and loaded on. Safety margins are stringent.
We have to look very carefully at the weather, so we have a very strict weather limitations. For this cargo, every cargo will have a little bit different because it will depend on its size, on its weight. In this case, our limit was just 15 knots wind, which is not that much. It was a wave that was not more than half a meter, which is also very little. And also the current, we are on a river, so also the current, which is not stronger than 1 knot.
Loadmaster Bartosz, who is leading the operations, prepares for transfer to the Hawk semi-submersible, which must wait for loading far from the busy port of Vung Tau. He boards a small boat that will bring him 10 nautical miles out to the Hawk's position. The Hawk's crew is already busy on deck preparing the wooden beams on which the load will be balanced and then modified based on the measurements made after inspection. On the main deck of the Hawk, the captain, Pawlo Rewucki, awaits Bartosz's arrival. The captain lives every day of his work in the heavy lift sector as an opportunity brimming with memorable experiences.
For me, it was very interesting how different type of the cargo can be transported by the vessel. So the job is not only, how to say, 3 months contract. You should do something new, study, and you should grow in professionally on board the vessel all time.
The countdown continues. Less than 24 hours remain before the lifting maneuver begins, so it's time for yet another logistical meeting of the team, this time with the crew and captain of the Hawk and the assisting vessels and tugs. Will the weather hold? For the operation to be safe, there cannot be storms in the forecast, but it seems there are more clouds on the horizon.
For loading, we will first bring the cargo alongside the vessel by tugs. Then we will try to hold the cargo in position near the ship. The final positioning, we will, in this case, we use guideposts, we use paint marks. We have a theodolite, and with the theodolite we just make sure that the vessel is exactly in the center of the vessel, so designed position in this case. In other cases, for other cargoes, we might use different methods for positioning, and that might be cameras, underwater cameras, might be verified by divers, also stoppers, which is welded to the vessel. So each cargo will have a slightly different method for positioning.
Bartosz and the chief officer check on progress along the deck. The laying down of wooden beams must be precise, because the load, once the refloating has happened, will be directly resting on the deck. Bartosz heads to the center of the ship, where a theodolite device is mounted. He dials it in, making sure all the settings are correct to help him with the alignment.
And with this device, we will make sure that it's actually in position that we want the vessel to be. We have few methods to guarantee that the units are in position. We use guideposts, which are welded now to the deck. Some paint mark system, which is painted on the unit itself, plus the theodolite. And then, of course, after the vessel will deballast and the deck is dry, we will confirm again everything visually to make sure that we are within the limits that we want it to be. Typically, it's approximately 1 inch accuracy while loading the cargo and positioning over the deck.
The trip through the Arabian Sea and onto the Black Sea to the unloading position in Burgas, Bulgaria, will be long and full of uncertainties.
To submerge the ship, we start everything from basically inspection of the deck. We have to make sure that and there is no any loose items on the deck, so that everything is well secured, so that when we submerge, that nothing will be floating, there will be no garbage around the vessels.
With no break in the weather on the horizon, Bartosz makes the call with the team to delay the operation. They must wait out a storm arriving in the coming days, which is likely to make the sea too rough to operate inside the busy and shallower port area. The Hawk heads out to a safe position in deeper waters to weather out the storm and wait for a window of clear skies that will allow the operation to be green-lighted. OHT, Offshore Heavy Transport, is a Norwegian company specialized in hiring out ships to transport heavy loads such as jack-up rigs, bulk carriers, or other massive ocean vessels that must be moved from point A to point B. These amazing semi-submersible ships carry some of the heaviest objects plying the seas.
The free deck space, so it's 157 meter long. The beam is 55.5, but the beam does not restrict the size of the cargo that we can take. We took a cargo which was 100 meter wide, so we had an overhang of 25 meters to each side. We are restricted by the length of the deck in this case, and we need to have a little bit of space when we bring cargo. So in this case, the longest cargo will be approximately 2 meters shorter than the actual length of the free deck space, in this case 157 meter.
Running a massive ship like Hawk depends on extremely powerful diesel engines that must be able to propel a ship whose weight while sailing can be up to a whopping 83,000 tons. Chief Engineer Josip Majnaric does most of his work down here in the bowels of the ship.
Now we are located in engine control room. From here we can operate with main engine and auxiliary engines. We have operator panel, main switchboard where generators are connected, and we can full observe condition and running and all parameters for main engine and auxiliary engine.
The Hawk is just one of 5 offshore heavy transport ships working in the sector, where dozens more ply the seas.
We have at the present moment 5 vessels of this type. This is the biggest one that we have. This vessel can, the dead weight of this vessel is around 65,000 tons. So what we can carry, the biggest cargo that we can carry will be in the range of 50,000 tons in weight. What's more important, we can take approximately 30 tons per square meter on a deck that we are presently standing on.
The sheer enormity of these heavy load carriers is even more impressive if we compare them to objects or areas we are more familiar with.
The vessel is approximately 223 meters long, with 157 meters of free cargo deck space. That will correspond to approximately 1.5 football field lengths, which is quite impressive, actually. The weight of the vessel, empty ship, I mean, it's just a steel structure, is approximately 27,000 tons, with the transit condition of approximately plus minus 83,000 tons, which corresponds to more or less 500 Boeing jumbo jet planes, which is even more impressive. And when the ship is fully submerged, ready for loading, the weight goes up to more than 137,000 tons, which is 800 jumbo jets. So it's really, really impressive when you put it in perspective.
We have one main engine on the ship. It's a two-stroke main engine, MAN Maker. It's a slow-speed engine on maximum 85 revolutions per minute, giving total power of 13,300 kilowatts, or what is actually equivalent with 18,000 horsepower. It's quite strong engine, but it is very reliable.
Sometimes it looks like easy running, but even the pilot not fully understand how it's difficult to stop this 220 meters. Sometimes it's not possible to stop within few minutes. You should adjust your mind and be worried about this. We can run very fast, but to stop the vessel it takes time.
But how exactly does a semi-submersible ship actually work? The ship is able to lower its deck to below water in order to float its cargo on and off using a specially designed ballast system to empty and fill the tanks up to just a few centimeters of air pockets. Key to any heavy lift operation of this magnitude is what happens in the ballast room, which is where the most delicate phase of the operation is carried out. The chief officer, Vitaly Smirnov, supervises on deck but is in control of the ballast room operations.
So we use for eject the water from the tank for ballast pump, 3,000 tons per hour capacity, and one big one with 4,000 per hour capacity. And for stripping water from the tanks, we use a GS pump, the small one, just for stripping of the water, for prevent the free surface inside of the tanks.
To submerge the vessel, the crew start filling up the dozens of ballast tanks until the main deck is almost underwater. This is a very critical stage, because with water moving freely around in the tanks, the vessel loses its stability.
The ship has 81 ballast tanks, this, with total capacity about 140,000 metric tons. And all tanks we are using for the loading and discharging operation. This panel shows the all tanks. The ship has three levels of the tanks: upper, middle, and lower. And the same three lines: the starboard, port, and the center line. But additionally, about 4 years ago, was installed on the shipyard sponsons tanks from port side and starboard side.
This ability to sink below the water's surface in order to take any cargo on board has made the Hawk a sort of ocean-going ambulance, ready to come to the rescue of some of the largest behemoths of the high seas. On the morning of August the 8th, 2016, shocked residents of Dalmore Beach on the island of Lewis, Outer Hebrides, woke up to find an orange steel monster washed up against the rocks of their wild coast. A massive 17,000-ton oil rig had appeared out of nowhere. Photographs of the Transocean Winner quickly went round the world, the spectacular barren beauty of the place contrasting with the environmental hazard the rig represented. First, the Transocean Winner was refloated, then tugs towed it to a deeper, safer place in a quiet bay, where the OHT Hawk came to the rescue to take the rig away. 6 weeks after the Transocean Winner rammed ashore, the Hawk sank until tugs could drag the wrecked rig over its sunken deck. Then, once it had recovered buoyancy, successfully sailed away with the massive oil platform fastened securely to the deck. A few months later, Hawk was called to her next assignment, perhaps the biggest yet, to load the Askepot, a Cat J70 jack-up rig, one of the biggest in the world, after its construction was completed in the Samsung shipyard of South Korea.
The biggest cargo this vessel carried so far, it's jack-up rigs, Gusto MSC CJ70s. They are approximately 40,000 tons, plus minus. The biggest one we took, it was actually 42,000 tons during the float-on operation, with dimensions almost 100 meter wide and 130 meter long, including the helipad, and 200 meters of legs on it, so quite impressive. And it was also the biggest cargo I have ever carried, loaded and discharged in my career.
The Askepot is a 3-leg cantilever-type jack-up rig. It had been built for Statoil to do deep drilling for production wells. These amazing super rigs can operate in water depths from 70 to 150 meters and drill wells as deep as 10,000 meters below the seabed. The jack-up legs are an amazing 200 meters tall, second tallest in the world. After it passed its height test in the impressive Samsung shipyard, Bartosz and Hawk could start working on the 30-hour loading operation. It would then be transported by Hawk from South Korea to Norway, a journey taking several weeks. How long each journey takes to transport mega objects from point A to point B on a semi-submersible ship depends on how heavy a cargo it is carrying and what kind of weather conditions these amazing ships that carry ships encounter along the way.
The speed of our vessel will depends cargo type. Different cargo, different speed, and also weather condition. But average speed will be around 12 knots. Regarding the time of cargo operation, is also vary from cargo to cargo, but actually we require it around 1 week to load and fix the cargo for sea voyage.
We have a stop work policy in place, so everybody can stop anybody, regardless of the rank. So lower ranks can stop the higher ranks. You know, the captain can be stopped by ordinary seamen, if necessary. And we prefer to stop just to make sure that we reduce the risk to minimum. Again, to be sure that the people are safe, that the cargo is safe. So better be safe than sorry.
Bartosz is careful to put safety first. Safety of the crew, then safety of the cargo, and finally time pressures, which are important but not at the expense of safety. Handling such massive objects involves a lot of risk that must be managed.
We moving big objects, we heavy objects. We use a lot of machinery. We use a lot of equipment in a process to do that. So of course it is risky. But again, we try to plan everything. We try to have toolbox talks with all parties involved. We try to explain what we want to do, how we want to do it. We don't try to rush things. So we prefer to stop the operation.
Heavy lift loading can take from 3 days to over a week, depending on how complicated the operation is. This time, Hawk is operating in a shallow and congested Vietnamese port, where tiny fishing boats and nets are present alongside massive ocean-going vessels. There is a difficult river current here, as well as wind and swells from the monsoon season.
As soon as we have required depths, submerging depths, and weather permitted, we can start loading operation. Loading operation will be performed with tach assistance. The cargo will bring alongside with tach assistance. After this, when the cargo near our vessel, we will take care about the cargo. We use our cargo lines and bring the cargo to exact proper position as per manual and drawing.
The operation has been delayed for several days due to heavy monsoon rains. But finally, a break in the weather is on the horizon. Loadmaster Bartosz decides to go forward with the operation the next day. The night before, he holds a planning meeting to go over every last detail of how the loading will proceed. He will be the first man up, giving orders on the bridge at 4 a.m., with crew on standby soon after and ready for 6 straight hours of work from 6 a.m. on. Each man must have life jackets, water and rain gear available for the duration of the operation.
We start tomorrow morning. The first unit will be alongside 6 o'clock in the morning. I think stand by everybody 5:30.
Each crew member is assigned one of 8 ropes that must be fastened just right to slowly maneuver the cargo ships into place. The ropes must be knotted and looped and fastened correctly so that just the proper amount of slack is present at all times.
For Valentin and for Robert, you are our brakes, eh? So do not slack too much. So you are slacking only little by little. Probably we will tell you half a meter or 20 centimeters, no more.
Then the stoppers will have to be put into position, and they are allowed to barely kiss the delicate river vessels, Bartosz warns. Gentle touch. The ships will be brought out one by one every hour. There is no room for error. Any questions, he asks?
There are no stupid questions. Every question is good.
He reminds the crew of radio operations policy.
Please, when he will ask you or I will ask you something on the radio, repeat, okay? On the radio. So we know that we understand each other. That we don't have any problem. If you don't understand, just say, please repeat, and when we repeat. That's no problem. If necessary to repeat 3 times, we repeat 3 times. So no worries here. Yeah? See you tomorrow then. Have a good rest tonight.
Satisfied they have gone over everything, he bids the crew good night. Tomorrow will be a full day, and everyone must be well rested for the operation to start smoothly. Dawn breaks over the port of Vung Tau. It's a new day, and the weather permitted the Hawk to move into position inside the port during the night in order to submerge in preparation for loading. The morning sun reflects off the water where the entire length of the Hawk's deck is completely submerged. The tugs are in position, the same place as 2 days ago, and ready to start towing their ships to the loading zone. There may seem to be no hazards, but there are many hidden dangers that the crew must be on the lookout for, now that the massive Hawk is operating inside the busy, shallower port.
Yeah, it's not, how to say, easy place. We have plenty fishing stakes around, small buoys, small vessels. Now southwest monsoon start, so heavy rain can start within few minutes, and it's heavy predicted situation. So the vessel should be ready in all respects, engine should be ready all time, and the crew should be ready all time. It's not easy place and quite close location. But we have no other possibility to load this cargo. this is only one place where we will manage to load.
The first vessel is being towed by 3 tugboats, but port traffic delays its arrival. It is not easy to navigate this labyrinth of large cargo ships and tiny fishing boats. Bartosz and the chief engineer reach the first ship to follow the operation directly on board, one on the stern and one on the bow, directing the crew that remained on board Hawk, as well as the small supply boat that will bring the many ropes used to pull the vessels into position and then ratchet them tightly onto the deck. The first line is attached to the Hawk, but immediately the loadmaster is presented with a problem. Rough seas begin to complicate the situation. The job gets delayed from the outset, and the swells are not making it easy to use the system that alternates the ropes between bow and stern, using a total of 8 different lines to best position the first vessel. The most important because it is the vessel used to align all the rest of the load. But the sea shows no intention of calming down, and the crew is encountering double the difficulty in every operation they undertake. Bartosz doesn't hold back and is on the front line of every action. The method in which all the ropes are anchored to the cargo via the Hawk's guideposts assures not only correct alignment, but above all the stability of the load during the long, dangerous voyage it must make to Bulgaria. On the Hawk, the officers are staying in contact with Bartosz as they play tug-of-war with the ropes in order to allow the proper tensions and slack. Everything is proceeding based on very small margins of balance that the loadmaster must direct thanks to the precise measurements made in the days prior and, of course, to his many years of experience. Once the first vessel is in position, finally the crew can begin to load the second ship.
During loading we had approximately 13 knots of winds, between 12 and 13, so it was already quite close to the limit. On top of this, the wind was blowing against the river that was also building up a little bit the wave. So the wave was again on the limit, almost. And then they missed the slack tide by 2 hours, and we were loading almost maximum allowed current in this case. So strong current, strong wind, wave, and the boat is quite small, so they were really struggling to do it. And again, you know, I prefer to do it slower in this case to make sure that the guys on the boat are safe.
This time, the rubber service dinghy leaves from the bow, and the chief engineer is in command of the operation to bring the cable over to the vessel. Now that the seas have calmed, the work is going more smoothly. The winches are working at maximum power to give enough rope to bring the second vessel to the center of Hawk. Every unit waits its turn to let go of the rope and then reattach it. Under the hot midday sun of the Tropic of Cancer, the second ship is also finally aligned and connected with lines to the first ship. It appears that the operation, up until this point, is going well. Now the theodolite must confirm perfect alignment with the marker painted down the center of the ship. The heat is unbearable. The crew decides to take a break. After the break, the third vessel finally arrives. 2 vessels have already been connected. Now the crew must use first 2 ropes with precision to bring the third vessel into position as well. Fatigue is starting to set in, but there is no time for distraction, as the sea is once again being whipped up by the wind. With thousands of tons of water in its ballast tanks and 2 of the 3 ships loaded, every precaution must be taken to complete the operation safely and successfully. A single error made now could cause an unthinkable accident inside the congested port of Vung Tau. Not just cargo, but lives are at stake. Gradually, the third vessel is also brought into position. From the bow, the crew returns to the stern of the ship via a long, dark tunnel that crosses the deck. Once all three ships are fastened down tight, it is time for Hawk to start the refloating. The work is complete and on time. Now the crew of the three vessels, after having stayed on the Hawk during the deballasting to refloat the ship back to normal levels, may return to their own rooms on the ships being transported. One more check is made to make sure the three vessels are properly bound and anchored onto the Hawk before the crew prepares to leave port and go 10 miles out to deeper waters where the final sea fastening will take place. Meanwhile, the ship's captain is meticulously preparing their planned route.
The cargo will be discharged in Burgas, Bulgaria. We will have few interesting places where the vessel passing. At first we are crossing Singapore Straits with heavy traffic. Next critical point will be Red Sea with Suez Channel, and after this Dardanelles Strait and Bosphorus Strait. So it's quite interesting voyage for navigation and for our officer and engineer.
The OHT Hawk takes to the South China Sea to face the long and arduous voyage for one of the largest ever ships that carry ships. Nearly a month later, the Hawk sails into port at Burgas, Bulgaria, to unload and deliver her precious cargo. The fully loaded OHT Hawk rarely goes unnoticed. Each float-on and float-off operation is an impressive feat of marine engineering and heavy lift transport. Another month at sea, another mission accomplished by Bartosz and the crew of the ship that carries ships.
These buildings are among the biggest man-made objects. They have been moved many kilometers across the sea and sunk down to incredible depths. They are made of reinforced concrete, built in massive mobile and floodable construction sites, then tugged to their final resting place. Troll A is the world's tallest building, and the Gullfaks C is the heaviest object ever moved. They were the first in a long line of massive oil platforms built over the last 2 decades that use gravity and suction to remain upright in the stormiest of seas. But it was the Hebron project, whose 65,000-ton topside was the biggest ever moved when it was towed from Korea to Canada, that broke heavy lift records when the whole whopping 750,000-ton megalith was finally maneuvered into position. Oslo, Norway. This is the head office of Kværner, famed the world over for its concrete megastructures. Everything it builds is big. Indeed, it has built not only big oil platforms, but the biggest. Far out in the North Sea are 2 oil and gas fields, the Troll A and the Gullfaks C. Resting above them are two of the world's largest structures, respectively the tallest and the heaviest. Off the coast of Newfoundland, two other platforms, the massive Hibernia and Hebron, moved into place in spectacular fashion. The Hebron has the biggest topside in the world. When construction on the massive structure was finished in Asia, it was towed in a mega move halfway around the world to be installed onto the platform base in Canada. Kvaerner is specialized in gravity-based supports, massive concrete bases that use gravity to keep an oil platform perfectly in place. Some of these concrete giants float and are held in place by cables, but others simply lie on the sea floor. Not so simply, as we shall see.
Hebron has the heaviest topside ever installed, so it's 65,000 tons weight when it's operating.
Hebron, the last one that was delivered last year, is 133,000 cubic meters of concrete. Troll is 220,000 cubic meters of concrete. And Gullfaks Sea is 240,000 tons of cubic meter concrete. When it comes to concrete, because concrete is a bulk material, that is always numbered in cubic meters, not tons, when it comes to comparing sizes and so on.
The wild North Sea and northwestern Atlantic Ocean are among the harshest environments in the world. And yet, it is here where some of the most strategic oil and gas fields lie. Icebergs, earthquakes, and winds up to 100 kilometers an hour are just a few of the dangers that await the brave few who venture here. Indeed, the first freak 25-meter wave was recorded in the North Sea on an oil platform. This is the bustling modern city of Oslo, Norway. One of the great centers of the Viking explorers who braved the North Atlantic in open boats to discover the Americas, a historical connection that still ties Canada and Norway. Oslo was also the home to Roald Amundsen, whose ship Maud has recently been saved from the great Canadian North by adventurous salvors. The two countries share a unique understanding of the Arctic North and have learned how to build enormous structures that can survive in the hostile environment. For 3 decades, Norwegian, British, American, and Canadian companies have drilled the seafloor here to extract the black gold. At the heart of the operations was Kvaerner, one of Norway's most experienced oil platform design companies. Kvaerner's story starts in the mountains near Oslo more than 150 years ago, when water mills provided essential energy for manufacturing. With the Industrial Revolution, Kvaerner and their competitor at the time, Aker, began building ships, turbines, stoves, and tools to supply Norway's industrial development. When the North Sea oil fields were discovered at the end of the 1970s, both companies started building oil platforms. They specialized in a type of oil platform called a condi, a concrete platform that sits on the bottom of the sea, using gravity alone to stay upright. In 2002, the two companies merged, and in 2011, Kvaerner was split off as a pure engineering company focused on designing and constructing oil platforms. Here in Fornebu, near Oslo, at the Kvaerner headquarters, Catherine Rusten Haldorsen and Guro Løken work to see that the oil platform projects are not only built safely, but floated to their site of operations successfully.
I'm responsible for marine operation and decommissioning in Kvaerner. So when I joined the company back in 1996, we had just finished towing out the Troll A platform, which is often referred to as the 8 wonders of the world. So I thought that was just amazing for me as a young engineer coming, seeing this operation. And for Troll A, as you might know, it's 472 meters tall. So if you compare that with the Empire State Building, that's huge. The Empire State Building is 442 meters. So for me, Kvaerner was a company that built and installed the most fantastic platforms.
I must say that the worst thing that ever happens is if people get hurt. We want our people to go home safe from work every day.
The engineers and designers at Kvaerner must be confident that no matter how big of a structure they build, they know it will float and survive even the most challenging weather conditions.
The reason why a concrete platform floats is actually that the uplift and the weight is equal, and then we get it to a floating position. You might know about Archimedes' law, and that's the basis for all of this. Basically, when Archimedes put himself into a bathtub, he saw that the displaced water was the same amount of as his weight, basically.
The traditional laws of physics remain the guiding principle, but it is the tried and true engineering experience that assures the platforms are built to last, whether in the ice-clogged North Sea, the northwestern Atlantic, or the placid Adriatic. The North Sea oil fields were first discovered in the 1970s, just as the world was undergoing its first great oil crisis. However, getting to drill there proved a Herculean task. The Norwegians had a solution. The Condeep is an incredibly deep concrete structure that lies on the sea floor and holds the oil that is pumped in massive reservoirs. Catherine Rusten Haldorsen is the head of concrete constructions at Kvaerner and has seen many Condeep sail out of Norway's deep fjords.
Condeep is a concrete deep water structure. And the concrete platform may include oil or gas storage inside, 1 to 4 shafts, mechanical outfitting, and of course drilling equipment. And of course one important feature is it is the foundation for the topside. But I think maybe that in the very early stages, you know, with the extreme water depths, they did not have the technology for anchoring structures to the seabed. Today you see a bit some other solutions than what we had in the early beginning of Condeep platforms.
One of the most challenging oil and gas reservoirs is the Gullfaks field, 175 kilometers northwest of the Norwegian coastal city of Bergen. In the 1970s, 3 Condeeps were built to extract oil, but the last Gullfaks C proved to be a record breaker. The sea floor of the Gullfaks oil field is made of meters and meters of soft clay with the consistency of yogurt. The place was a slope down to the Norwegian Trench. getting at it was incredibly difficult.
Well, of course, if you have a very solid ground, stable ground, you don't necessarily need skirts. But of course, if you have a soft, more yogurt type of soil, you need to ensure that the platform is anchored well into the seabed. And you may use grout and of course air evacuation system to get the trapped air out from the structure.
Protecting the sea from pollution and humans from accidents has become an overall priority for all companies all over the world as oil tankers, wells, and platforms have grown bigger.
It's now clear the explosion that ripped a North Sea platform apart was the world's worst oil field disaster. A task force of naval and civilian ships is still searching 700 square miles of sea around the Piper Alpha platform tonight.
Exxon Valdez, gouged by a reef, more than 8.5 million gallons poured into Prince William Sound, a prime fishing and recreation area.
Frantic efforts underway right now to try to prevent an environmental nightmare along the U.S. Gulf Coast.
Construction techniques in the North Sea and open Atlantic today build on experience from the past to keep workers and the environment safe from such hazards. Platform moves are meticulously planned in simulation centers, for example, and there have been advancements in the core materials such as concrete so it holds up in harsh ocean conditions.
The salt water around the concrete is absolutely no problem. Basically, the concrete does not absorb any water. It's very dense and very waterproof.
In order to ensure that the Gullfaks sea platform stayed stable and upright, Norwegian contractors' engineers came up with the idea of building concrete skirts that would sink into the clay for 34 meters to provide the horizontal stability and anchoring. They would be sucked into the mud and held in place by concrete grouting that would fill any spaces left for the vacuum to leak. It was an ambitious project and required more steel than it would take to build 15 Eiffel Towers and 200,000 tons of concrete. Construction began in 1986 in a 14-meter deep dry dock. Many months later, the 16 concrete skirts had reached the required height of 34 meters. Then came the construction of the bottom of the oil reservoirs, again, more steel and more concrete. When no more could be done on the land site and the construction yard was flooded, the base of the Gullfaks sea oil platform was floated out into the fjord. The Norwegian fjords offer platform constructors a unique advantage because they are deep. Even deeper than the surrounding mountains are high. The base of the platform was surrounded by barges and boats, and now the upper part of the oil reservoirs could be completed, and then the 4 massive shafts constructed on top of them, slightly leaning inwards to better access the wells and for center of gravity. Now that the construction was complete, the first of the huge lifts that would turn this mass of concrete into a platform could begin. In order to do this, the 330-meter-tall structure had to be towed through the fjords of Norway from Vats to Stord, where the topside was awaiting it.
When we are designing these platforms, of course, you need to make sure that you have something called the center of buoyancy for the platforms, and you have something called the center of gravity for the platform. So when we are designing platforms, we have to ensure that we have sufficient stability for towing these platforms out. If the stability is not big enough, then you start rolling and you might actually tip over. I mean, basically, when we do tow out of platforms, we have to ensure that we have a positive GM, is what we call it, geometric metracentric height for the platforms.
This is the most delicate moment of the whole construction of the Gullfaks platform. The concrete towers need to be sunk so that just 7 meters are protruding from the sea surface. This means that the narrower sections of the 4 shafts are under more pressure of water than they were designed for. So, any sign of cracks or leaks would stop the whole operation. It is thoroughly checked as the barges carrying the topside move slowly towards the shafts. The fleet of barges and tugs approaches the concrete structure, and compressed air is pushed into the barges to lift them to the required height. When they are over the structure, they can be reballasted, and slowly the topside sinks onto the towers, the mating complete. Now the whole platform could be raised to its full height out of the water, and pressure on its sides eliminated. A dozen tugs with 160,000 horsepower were needed to move the behemoth, featuring a displacement of 1.5 million tons.
Gullfaks is the heaviest object ever moved. It's 1.5 million tons. So if you have 1.35 million mini beetles, that is what you're actually towing out. And you can imagine doing that with 12 vessels, maneuvering these through the narrow channels is a fantastic sight. You also have to remember that when you have 1.5 million tons moving, it's not that easy to stop it. So that's why we have to do it slow and in a controlled manner.
The Gullfaks sea platform was towed slowly through the fjord out to sea by tugs. On the 8th of May, 1989, it arrived on site despite heavy seas. Oil pipes had already been laid to other platforms in the field, so it had to be positioned perfectly. Water was used to ballast the skirts evenly. Slowly, suction devices pushed the skirts more than 20 meters into the clay. Any gaps were filled with concrete to keep the vacuum perfect. But the records set by Gullfaks sea platform were to be shattered by a new Con-Deep built in Norway 10 years later.
A concrete platform that is placed on the seafloor, like Troll and Gullfaks, you can have enormous topsides. So, of course, if you have a floating platform, it's limited how much weight you can have on board. And because if you have a huge, the bigger the topside is, the bigger the hull has to be in order to keep floating, basically, to get enough buoyancy. So often, I mean, when, like in the North Sea, you see that you have around 300-400 meters. We often have Con-Deeps, as we have explained, but when you go 400 or 500 meters, we end up with the semi-submersible or TLPs, like we have on Heidrun, or FPSO, like you see on Varg and other fields.
If Gullfaks was big, then a decade later, the Troll A project was even bigger. At 470 meters tall, it was, at the time, the largest ever energy project supplying Europe with clean natural gas. The Troll gas field is located in the Norwegian Trench, so even deeper than the Gullfaks oil field. The platform that Aker designed and built in its Stavanger plant became the tallest building on the face of the earth. Here too, the platform was designed to be kept in place by concrete skirts that would dig deep into the soft sea floor, sucked in by vacuum. However, although the technique had been tried and tested before, Troll A's height posed some serious problems for designers. The Norwegian fjords, in their stark beauty, are the legendary home of Norway's favorite monster, the troll. The name of the deepest and most dangerous natural gas field, therefore, seemed appropriate, and the monster that Aker, Kvaerner's sister company, built fits the description. It was designed to resist the highest waves, the worst storms, and even earthquakes. The Aker dry dock in Stavanger is the site of construction of the skirts of the Troll A platform. Now came the time for the very first of the towage operations that made the construction of Troll A and its positioning on the sea floor such a spectacular event. The dry dock was flooded, and the huge concrete structure began to float. It was towed out to the adjacent fjord to be continued. Out in the fjord, the oil reservoirs were covered with their dome caps, and construction began on the shafts. However, once they had reached 60 meters in height, the platform had to be moved again. The fjord here simply was not deep enough.
Basically, part of the concrete platforms is always built in a dry dock. And depending on the total height of the structure, it could be completed in the dry dock, but very often we have done the first part. Then it's being towed out to a deep water site where the remaining structure has been completed. And in some cases, the topside deck is mated in the deep water sites. We try to do as much of construction in the dry dock as possible. Constructing in a deep water site does increase the cost because of all the flotilla, all the barges we need to maintain offices, services and so on in the floating stage.
Construction was fast, as the company employed a new technique known as slip forming, which minimizes the time it takes for concrete to dry, making for a smoother and stronger surface. Once the deeper fjord was reached, the box girders that served to harden the very tall structure were built. These were prefabricated steel structures that were then encased in concrete to stop the four shafts from swaying with the waves. In the meanwhile, workers got on with building the ancillary equipment, the pipes and tubes, electric circuits and gauges.
The majority of the construction method is based on slip forming technology. It's an hydraulic system that lifts up the forms, and the reinforcement and the concrete is being executed 24 hours a day. So weekends, Christmas, all days. This is, has many advantages, and that is you reduce the amount of casting joints. So in principle you get a better quality, you get a watertight structure, and of course it's quicker to build. So you save overall construction time for the projects.
Troll A was designed so that the deck was long and narrow, keeping living quarters far from the derrick and working area as an added safety measure. This, in turn, means that the drill shafts are central, while two support shafts are external. As construction continued, the shafts were sunk deeper and deeper to allow better access to the segment under construction. Then came the third great heavy lift operation of the whole project. Time had come for the concrete support to be mated with the deck and all the equipment it carried. The concrete was sunk to within just 6 meters of the top, so subject to far more pressure than it was originally designed for.
For the platform, we have like permanent ballast system in the platform. But in addition, for these temporary phases, we have some temporary ballast pumps so that these operations can go fast enough. Because we need to be, normally these operations are weather restricted, so we need to do it within a weather window. So we use ballast pumps, pump in water, pump out water in order to get out of the dock and also in order to mate the topsides on the platform.
Barges carried the long, narrow deck out to the shafts and were pumped with air so that it could be safely fitted over the 4 shafts. Every connection had to be fit perfectly for the mating operation, which was completed in 30 hours as the barges were emptied of air and the deck lowered. Once the connection had been made, the whole platform could be refloated to its full height. The refloating and towing is usually done when the North Sea weather is at its fairest.
We never know exactly what wind and waves we see, but on board these huge tows, we normally bring a meteorologist with us, and we have weather meetings several times during the day in order to make sure that it's no hurricanes or no unforeseen weather coming up. Because then we have to either go into a safe harbor or hold the towing fleet for a while. When we do plan these operations, we do it during summer season in order to make sure that the weather is nice and we have predictable weather. But it's, I mean, what can I say? We need to do detailed engineering, and then we have it under control.
Higher than the Empire State Building, as tall as the Petronas Building in Singapore, the Troll A was the tallest man-made object ever to be moved. On the 10th of May 1995, the tow out to the Troll gas field began.
First of all, you have to maneuver your platform out from the dock where it's constructed. Then you fill water into the dock, and then you have to fill water into the platform so that it doesn't have uncontrolled liftoff. And when you go out of the dock gate, we often have harbor tugs attached to the platform. In addition, we have a towing tug getting us out from the dock gate, and we also hold back with something we call hold back winches, and then we can ensure that we go smoothly out of the dock.
These massive platforms must be towed very slowly out of the dock and maneuvered in a very controlled manner out into the towing channel, never faster than 2 to 3 knots. Today, tests are done at a simulation center, first to make sure that all vessels are towing with the right amount of force to navigate the route successfully. But there must also be a clear chain of command.
So when we have decided what vessels we're going to use for the tow, we invite the captains, and also we always have a tow master. He's kind of the, if you're in the military, you have to have one guy that's in charge of the tow. So he's in charge of the tow and he's giving orders. So what we do is to rehearse the full operations, both the inshore tow and the offshore tow, with all the involved parties, so that we make sure that every small, like you asked, if we're going through a tight corner, we need to make sure that that vessel pulls in the right amount of force.
Tugs began moving the Troll A down the fjord. They had been over the route several times, virtually. The course took the convoy round a very steep bend, but also at some points the clearance between the seafloor and the bottom of the platform was a meter only. An uncharted rock could have stopped the convoy in its tracks and threatened to topple the platform. It took 7 days to go 200 kilometers. The heavy concrete bottom compensated for the tall structure, and when it was over the designated area where gas pipes have been laid, the skirts were slowly deballasted, keeping the whole structure vertical at all times to make sure that when it reached the bottom of the sea, it would sink evenly. In 1996, when it began operating, the platform set the Guinness World Record for the largest offshore gas platform.
Troll was designed for 70 years lifetime, which is extremely long. But of course the design principles and construction methods are similar. But of course continuous improvement and development of both design and method is very important to adapt to new standards and codes today.
A few years later, Aker and Kværner merged, and their engineering expertise was recognized the world over. In recent years, Kværner has worked on a number of mega projects that have shown that Norwegian know-how in maritime and hydrocarbon affairs is second to none. Kværner has built concrete and steel, oil and gas platforms everywhere in the world, but its speciality is concrete. Here on the Adriatic coast lies one of the most recent projects, specially designed to be low on the horizon and invisible from Venice.
One of the benefits with Adriatic LNG is you have established a fake island away from the shoreline, so it basically does not disturb the people and the region there. The terminal itself was built in Algeciras, southern Spain, and towed to Italy. But the two concrete mooring dolphins, which is part of the LNG, was actually built in a ship dock in Venice and then towed out to the platform. The topside was installed in Algeciras in southern Spain and then completed offshore Venice.
The massive terminal is a liquid natural gas regasification plant, one of the largest in Europe, that supplies natural gas delivered by ships to the city of Venice and the industrial port of Mestre. While today's platforms may not break records like the Gullfax or Troll A, they are still marvels of engineering, and there is no shortage of demand for oil and gas extraction platforms across the globe.
During the new concrete platform age since 2003, Kværner has actually delivered 5 new platforms in Spain, Italy, Russia and Canada. And I think that is something that is not necessarily so well known anymore. I mean, we tend to focus a lot on these, previous wonders, but concrete is as applicable today as it was during the Troll and Gullfax sea age.
One of the newest monster platform designs was actually built on the other side of the world in Canada. The Hebron and Ben Nevis oil field was discovered off the Grand Banks off Newfoundland in 1980, but taken more than 30 years to come online.
The concrete itself, there has been a huge development of concrete the last 20 years. Of course, concrete consists of cement, water, aggregate, sand and coarse. But there is also a lot of admixtures in the concrete. Or a lot is maybe not the right word, but there is admixtures in the concrete that could speeden up the hardening or slow down the hardening. It also makes it more fluid, so you can actually pour heavily reinforced structures. So I would say that with the development that has been within concrete last 20 years, I see there is hardly any limit on where we can go when it comes to high performance concrete.
Just the base of the Hebron oil platform is 122 meters tall and 130 meters wide at its base. It contains 52 wells and weighs 40,000 tons, made up of 143,000 cubic meters of concrete and 8,000 tons of structural steel and piping.
Hebron, for example, was built to 27 meters in the dry dock before it was towed out to deepwater site. But it depends on how wide the diameter of the platform is, and of course of the water depth in the dry dock. So we need a certain buoyancy to get off the dry dock basement and towed out of the dock.
The enormous base has the dual role of keeping the platform on the ocean floor and at the same time holding up to 1.2 million barrels of oil pumped from below the sea floor. Over the months, the huge structure began to take shape until it was ready to be floated.
Now, I say safety is an extremely important value for us in Kværner. And already in the early design phase, we start planning safe execution, and both for the construction phase, but also for the operational phase. Also, we are extremely proud of having executed Hebron, completed in 2017. We produced more than 23 million man-hours without any lost time incident.
As the huge platform base was floated out to sea for finishing, the second phase of the work could begin, the construction and later transport of the central topside, which included the drilling and utility modules. The dimensions rivaled those of the base, 183 meters long, 75 meters wide, and 113 meters tall, weighing 44,000 metric tons. But with the addition of the accommodation module and derrick, this will rise to 65,000 tons. The tools brought in to do the job were enormous. The des, or derrick, was delivered to the construction site by barge. Getting the derrick off the barge was in itself a delicate operation, as the massive steel building was a high center of gravity. The 3,900-ton drilling support system was delivered to the base. The steel units were delivered by barge and offloaded using SPMTs, or self-propelled modular transports. Transport engineers built 6 towers that were to hold the lifting and skidding system that were key to putting the drilling support system on top of the UPM. 16 strand jacks, each with a capacity of 750 metric tons, were mounted on the 6 lifting towers and attached to 2 35-meter girders, on which in turn held the 12 skid shoes and 2 kilometers of skid tracks that were key to the movement. The structure was skidded onto the Dutch-owned ship Blue Marlin using 64 1,000-ton skid shoes. These creep along Teflon rails like caterpillars, extending their reach hydraulically and then closing, pulling the load along with it. Now the UPM arrived and had to be offloaded. Here again, skid shoes were the key piece of equipment, and over 2 days the massive steel monster was moved to the shore. It rested on a finger surrounded by sea, allowing barges and tugs to access it with ease, and eventually the whole structure could be lifted onto the massive base, which had been specially designed to withstand the ice and storms of Canada's frigid north.
In Canada, you have challenges with the icebergs. So of course, those platforms are designed for iceberg loads. While other places, you have different kind of ice challenges that you need to design for. Some areas we have earthquake that we need to consider. And of course, the other environmental loads like wind and waves are key factors for designing the structures.
Over 2 days, at a snail's pace, the module moved towards its final resting place. Once it was in place, the lifting towers had to lift the second module, the 3,250-ton derrick or des, into place. The Italian heavy lift company had been engaged also to install the living quarters of the Hebron oil platform. Over the course of the months, the construction of the living quarters was completed in the huge hangar where 2 gantry cranes lifted prefabricated units onto the basic living quarters structure. The living quarter module was 58 meters long and 17 meters wide, no less than 30 meters tall. It was also equipped with a helideck that added instability. Like the DSM, it weighed 4,000 tons. Once again, the lifting towers were called into action and the strand jacks lifted their loads slowly but surely. The living quarter module was hanging from the towers, but needed to be installed at the correct height so that once floating alongside the UPM, it could be easily and swiftly installed. Fagioli built 10 support towers made of tubular steel and installed them on 12 transport beams. These were mounted astride 5 lines of SPMTs, and the whole unit was more than 40 meters high, with a center of gravity 30 meters high, and a tipping angle of just 8 degrees, an extremely unstable building. Now it had to be moved towards the barge that adjusted ballasting as it took on the weight of the living quarters. The living quarters approached the UPM. By the end of 2017, the massive utilities and processing module was ready to be once again skidded onto a massive barge. At the other end of the bay, the rest of the Hebron oil platform had been completed. Once again, the whole gravity-based structure that would one day rest on the ocean floor was sunk beneath the waves.
Well, any project and concept is unique. They are custom-made. First of all, they need to adapt to the water depth where they are placed. There is oil and gas storage needs. We have environmental conditions. We have the reservoir. And there may be also linked to other systems or platforms offshore or onshore.
The top side of the Hebron oil platform was floated over it and attached to the protruding central tower. Once again, the whole oil platform was refloated, ready to be towed out.
Every time when I see a group of people put together, doesn't know each other from before, executing projects like this in an excellent manner, that is a big moment, yes. But of course, towing out of structures when you see the work is completed is of course also a good feeling, yes.
Another sunset over the frigid north, where the demand for black gold, the precious natural resources that fuel our everyday life, buried deep beneath the sea, gives impetus to the most massive engineering on Earth.